So last time we talked about continuous bridges. Three-stress PT bridges. And these are also called spine beams. This is called a spine beam or a box beam. And then you can have T's, the double T's. This third. And so you can have double T's like this. But these torsionally less stiff. So what is the difference between a double T and a box girder? Box girder is torsionally very strong. So load distribution is very good load distribution. Here the load distribution is less. Where is the difference? Then I told you, if you have a simply supported beam, no problem, just put E and then equivalent to W. W is equal to 8 PE divided by S squared. And then I told you, if it is continuous, design is not that simple. And we have to find the profile to satisfy the M2 assumed is generated. M2 assumed is generated. Then I told you about how to find the M2 by using equivalent loads. Now these equivalent loads are used a lot for slab designs, and they can be used for beam design as well. And M2 can be found by using equivalent loads, but for that you need SAP 2000. And you have all the systems, you have all these loads. Then like that. So you apply all these loads onto SAP 2000. Then you will get a diagram like this. And then from that, you can get a bending moment diagram like this. Get a bending moment diagram like this. Right. So this is the bending moment diagram. And what is the effect of bending moment diagram? Like this. The effect of this diagram is to change the origin of the bending moment diagram. So you design for a higher moment here. You design for a lesser moment. And this is called MD with origin as this, and this is called MA. So we learned all these things, and then we learned another method to find the if you know the cable profile, we said so you have some profile. Already selected, and then to find the bend moment diagram, the secondary moments, we said we have to consider two systems. Beta j, so this is beta 2, this is beta 3. The support numbers are number 1, this is number 2, this is number 3, this is number 4. Beta always vary from 0 to 1 over the length of the span. Then this beta j, then we get beta I, is beta 2, but this is beta I, and another beta I like this, then beta I. And then we said the left hand side of the equation is beta I, beta j, P E dx over E I. And if the pre-specific force is known, then so this is not P is not E dx over E I. Because if you look at the note, see that the equation is beta I beta j dx, there's no E, beta I beta j dx over EI. So here you get beta j going like this, and beta I going like this at the first support, and the integration of this is this L1, L2, L3. The distances are L1, L2, L3. So you get this L1, this L2, divided by 6, L1 plus L2. Then the other integration is this one. This beta j or beta 2, and then you get the other integration is these two, this beta I. So this one and this one, you know the answer is this L2, this L1, this L3, L2 divided by 6. So for this you can work out the left hand side of the equation, 1/6 L1 plus L2, L1 plus L2, twice L1 plus L2, L3, L2. Here you get L2, here you get L2 plus L3 twice, and equal to integration beta P E dx over EI, integration beta P E dx over EI. So if I share the screen, you'll find that the right hand side is beta P E dx over EI, but these are beta j values, so this is beta 2 value, this is beta 3 value, right? So left hand side of the equation is not a problem at all. The right hand side of the equation is what we have to decide. So basically we get a profile like this. So P, you have to multiply it by P, E, and then you have to multiply it by beta, beta 2, So once you multiply, so we see how to multiply that. You get a file like that, and then you get beta going like that. So once you multiply these two, what do you get? You get something going again like that, coming to C. Now what we have to do is integration beta 2 T E dx over EI. So this integration means the area of this diagram. Integration of this side is area of this diagram. Now how to find the area? H1, H2, H3. Using Simpson rule. So here you get H by, and this part is H by 3, H1 plus 4 times H2 plus H3. There is a Simpson rule. Because Simpson rule can be used to find an area, and it can be used to find the value of this integration as well, because integration means area. So this integration means the area of this diagram. So this multiplied by this area of this diagram. So you get H by 3. If you have many sections, H1, H2, H3, H3, H4, H5, H6, what do you get? You get H1 plus 4 times H2 plus 2 times H4 plus 4 times H5 plus H6. So it goes like that. So basically these two, then you add these two, then you add these two. So you keep on going like that. So the equation for finding, so this coefficient we say this varies from 1, 4, 2, 4, 1. It goes on like that. The coefficient goes on like that. So in the spreadsheet also we have to arrange it like that to find the area of this diagram. So this is what I have done in this spreadsheet to find that. I'll share the screen again. So here you can see to find the area of this, to find the secondary moments, you can see here I have used. Marshall, you can see the spreadsheet. You can see beta varies from 0 to 1, 1 to 0. This is beta 2. This beta 3. So this should be actually beta 2. And this should be beta 3 because it's at the support number 3. And can you see S varies from 0, sorry, 1, 4, 2, 4, 1, 2, 4, 2, 4, 2, and it goes on like that. Can you see that? S goes on like that. Right, okay. And then, so you have to multiply to find the area. What do you do? To find the area, you have to get RP beta E1 beta 1 EP upper, EP lower. Why? EP upper. So you get two factors, and if you go to this side, in color. Have I got one more? Now you go to the so you go to the right hand side. You can see the sum C4 to AC40, AC40 up to this point. Sum AC4. So next one is sum C41 to AC41, C42 up to AC42. Right. So now you can see the values are minus 6, 1, 6, 7, 6, 7, 9. Other one is minus 3, 5, 1, 4, 3. So I'll stop here. So the matrix is, here you get 1/6, L1 plus L2, then twice L1 plus L2. L1 is 40 meters, L2 is 50 meters, 90, 180. And L2 is 50, and this is 50, and this is again 180. 40, 50, 40. Here you can see h by 3. H is 5 meters. So h by 3 is 5 by 3. So then you get on this here, you get M2, 2, M2, 3. So the matrix, if I write again, M2, 2, So you can find the inverse of this matrix. You can do it in a spreadsheet. And 2, 3 can be found, and the values that I found can be it's embedded in the spreadsheet. So if I look at this, M22 upper is minus 3126, M23 upper, 22 upper, M23 upper is minus 84. And what is the force? 29,000. So if I use 24,000, 26,000, I think that day we had 26,000 we used. And when you use 26,000, you can see this becomes 02 minus 60.59, and these are upper values. So which means so this is the wheel. So you get like that. Here you can get like that. So here you can get like this, and then we get the physical limits. One physical limit is another physical limit. So this is the upper boundary. This is the lower boundary. So M2 to upper, M2, 3 upper, M2 lower, M2, 3 lower. The values can be found, and if I share, so if I go this way, here you can see the values are minus 2102 minus 60.59. The low values are 4960 5153. Can you see this value? So you take these two values, there's a 0 in between. You look at these two values, there's a 0 in between. But this little tight, 60.59. So you get these values, the upper values at 2. Compare these two, you can get a 0 in between. You compare these two, you can get a 0 in between. That means 26,000 kilonewton P as 26,000 kilonewton is okay. That's okay. But what will happen if you use 24,000? Then let's say 25,000, not okay. Let's see why. So let M2 to upper, M2 3 upper, M2 2 lower, M2 2 lower. Let's substitute 24,000 in the spreadsheet. I'm going to substitute 24,000. Now see the values. Upper is 1, 413. This 602. This is 55465740. So stop sharing. So you can see the four values now. With 25,000. Have I got 25,000 or 24,000? So I have to substitute 25,000. The values are minus 1761, 480, 5236, 5489. So these are the values. And you can see when you compare these two, at 2, it's okay. At 3, both are positive. And we are searching for a 0. And we have 280 and 5489 and 0 is here. So however much you try, you can never find a bending moment diagram that can be fitted into RTEP values. RTP. So the reason is we fit a bending moment diagram which is RTEP. We fit it within this one. So we cannot fit it. So if you can't find a bending moment diagram, you can never satisfy all these boundaries. So that means P is not sufficient. P of 25,000 is not sufficient. P of 26,000 works. So what this means is diagonal diagram boundaries, diagonal diagram boundaries alone are not sufficient to find a P. Diagonal diagram boundaries alone are not sufficient to find a value of P. Even when the diagonal diagram is okay, P is not okay. So if you look at, I'll share the screen. We look at the graphics. Let's see, there's nothing wrong with the graphics. There's a small violation. No, this is line of task. See, this is a cable profile. There's no problem. There's a face everywhere. You get a visible region, and even at this support, we don't have a problem. You can see this. It's below. It's below, and this is just going there. So there's nothing wrong with 25,000. As far as the Magnum diagram is concerned. But this will not generate the same second bonus. Just see the values. See, actual is this 7969, 7967. Where are we? 25%. Ah, no, it will not change because we are not changing the profile. Right? It will not change because we are not changing the profile. So basically, it will generate. So basically, what matters is if you go for 26,000, the different condition. And now you can see the new values are pretty close. The new values are pretty close. So what you have to keep in mind is to find a proper to ensure that the stress limits are satisfied everywhere, finding a pre-stressing force will need additional conditions. Those conditions are not as simple as a simply supported case. Simply supported case, the moment you draw the manual diagram, it's done. You can select a pose. But in the case of continuous one, you have to do additional calculations to find where it satisfies. So this is a method. And now you can see why I have this factor called S. Can you see why I have a factor called S on the spreadsheet? You can see that. And then we use the same method, same technique to find all these different things. So because once you have concord, then we know the actual EP and then we know the actual ES. And here you can see, and if you look at EP actual, it will generate 0 secondary moments. EP actual, if you look at EP actual, it will generate 0 secondary moments. But yes, and then ES actual will generate the assumed secondary moments. And you can see ES actual due to actual, these actual profile, actual values. These are the selected values. They are pretty close. Mashita, is that clear? Is this so spreadsheet? I'm sure you can use because I have to make your life easy. I have done the spreadsheet, but to make your life difficult, I want you to convert the spreadsheet to your sign convention. So you can keep this as a master spreadsheet, but write the equations as we have discussed and convert it to compression positive and tension negative. And then you can't use 40, 50, 40 combination. You can go for 60, 70, 60 or 55, 70, 55 or what some combination. But I like to see different students using different combinations. Okay? Is that clear, Ashita? Right. So with that, we can bring the continuous bridges to an end. And shall we take a small break and then start? Shall we take a small break and then start discussing slabs? Is it okay? Okay. So I forgot to do a recording. Bhashita, are you doing a recording? Are you using some software and recording? Right. Then can you share it with Imanta? You know Imanta's number? I'll send Imanta's number. You talk to Imanta. Okay? Marshall, shall we start? Okay. So slabs can be one way, two way, or flat. So let's see how to design a one-way slab system. To take 1 meter strip and let's say slab thickness is span is 6 meters. Span is 6 meters. Slab thickness 160 millimeters. So in pre-stressed concrete, we can go in 10 millimeter steps. So we can have something like that. Here you need 20 millimeter power. Say 50 megapascal. 40 megapascal concrete. And the load on the slab is, what are the loads on the slab? Self-weight. 0.16 into 25. 4 meters squared. Finishers 0.75. Partitions 150. Imposed load 'So what shall we do? So if you want, you can draw Venn diagram and do it. It's simply one way span. But we look at how to use load balancing. So we say you have to first find the extensity. So if you take a cross section, so here you need 20 millimeter power. And we say the ducts are flat ducts of 15 millimeter. So here 80 minus 20 minus 15 divided by 2. Shall I say 20? It's 50. Emax 50 millimeters. And we say W is square root 8. W is square root 8 is P times C. And say we are going to compensate the full dead load 4 kilonewtons per meter. So 4 multiplied by L squared 6 squared divided by 8 P into 0.05. So P is how much? 4 into 36 divided by 8 divided by 0.05. 360 kilometers. And so let's say we are using 12 millimeter wires of 100 millimeters squared. So you get 15.2 of 140 millimeters squared and 15.7 of 150 millimeters squared. These are the commonly used strands sizes. So, so 100 millimeter multiplied by 1870 60, that is the breaking load for pasting 80 strands, multiplied by 0.7. Generally we stress up to 0.7, and the losses may be about 20%. The losses in slabs are lower, so the losses will be about 20%. So what is the force? 100, 1860, 0.7. So it can carry 104 kilonewtons. So the load that we need is 360 kilonewton load. So if you want, we can have double strands, can carry to 104. So 360 divided by 204. 360 divided by 204. And so if we provide these strands at 0.56 meter center to center, then we can provide the distance. So this strand arrangement can be every 0.56 meters, you have to have 2 strands. So now we have selected the strand, so we know the pre-stress, and this is the final pre-stress. And then, so we have an axial force of 360, and an upward force of 4 kilonewtons per meter, and we have a downward force of 4, and then we also have a downward force of 0.75. Then we have another downward force of 1.0. The line load is 5. So all this, the addition is 5 plus 0.75 plus 1.0. So we don't have to worry about the self-weight because self-weight is already balanced. So this is 6.75. Then we can say 6.75 kilonewtons per meter and 6 meters. So the bending moment is 6.75 into 6 square divided by 8, and that is 6.75 multiplied by 36 divided by 8, 30.375, and the Z value is 1/6 d squared, 1/6 into 1.0 into 0.16 squared, and that is 0.16 squared divided by 6, 0.00426, and MOVZ is 30.375 by 0.00426, 30.375 divided by 0.00426, 7,130 newtons per kilonewtons per meter squared, or 7.13 newtons per millimeter squared. So these are the stress caused by all these dead and additional dead and live loads. So additional dead loads are the load of finishers, load due to partitions, and then we have a live load of 5. So now we have to see what's going on. Now, because this upward force is already compensated. Now we have an axial force of 360 kilo newtons per meter. So 360 divided by 1000, 560. So we get 2.2 newtons per minute. So we have pre-stress of 2.25 newtons per meter square. So we have 2.25, and then we have this compression, this tension, this compression of 7.13. So what will happen? So you get minus 7.13 minus 4.88 newtons per meter squared, and here is the addition, 25 plus 7.13, 9.38. So here you can see there's a little bit of violation, because generally the maximum tension we can allow is about 2.5 newtons per meter squared in a class 2 structure. But compression stress is not a problem, because in slabs the pre-stressing is low, so you cannot have compression failure. So you can see now this has to be either, so somewhere here we have to provide some reinforcement to carry this additional stress. On the other hand, what you can do is you can design it as a class 3 member. So you can see one-way span slabs. We might need some high pre-stress. We cannot just compensate only the dead weight. So when you go for high pre-stress, what is the problem? The slab is cast like this. What will happen? It will lift up. So what I have done is, I have tried to see whether only the weight can be compensated. Cannot do that. So that means I have to go for a higher pre-stress. So what is the higher pre-stress I'll do? I cannot compensate only the weight, because this slab is heavily loaded. It's loaded with a 5 kilonewtons per meter square load. It's a crowd loading. So, but what will happen if the imposed load is only 2.5 newtons per meter square, like in office building? As in an office building, let's say live load is only 2.5 kilonewtons per meter. What will happen? What will happen? What happens is that if the live load is only 2.5 kilonewtons per meter square, then what is the total? Total is 2.5 plus 0.75 plus 1.0, 3.5, 4.25. Then what will happen to the bending moment? Bending moment is W squared of 8 is equal to 4.25 into 6 squared divided by 8. Then you get 19.125, and stress is equal to 19.125 divided by the set value 0.00426. You get 4.489. Now look at the stress distribution. 2.25 plus 4.489. 2.239. This side you get 4.489 plus 2.25, 6.4. Now you can see, okay, because you can take about 2 point. So we can allow about 2.5 to 2.8 type of stress in the slabs. So what this means, PT slabs are moved when live loads are low. So PT slabs are pretty good when live loads are low. So PT slabs are generally used in car parks, office buildings. But if you try to use PT slabs for something like a place where you can get crowd loading, then you have to think of going for slightly higher pitches. Is that clear, Bashita? So I have here used, for the first time I have used again, I have again used this load balancing method, and I have balanced the dead weight of the structure. And you can again see I have used a thin slab, 160 millimeters, 160 millimeters. So what are the advantages of this? Advantages are that, under normal situation, we consider that the slab is not cracked. If the slab is not cracked, what can you say about the second moment of area? Second moment of area is high. And if the second moment of area is high, what can you say about the deflection? Deflection will be low. So with 160 millimeter slab, I'm satisfying the reflection criteria over 6 meters. And to satisfy the deflection criterion with 160 millimeters, you need a lot of reinforcement over 6 meters. But here we are using only 12 millimeter wires at 560 millimeter center to center, 2 wires. So the advantage of PT is you can minimize the amount of reinforcement needed. And you have to understand this is a simply supported slab, not a continuous slab. So in a RC situation, you need about 180 or 190 millimeters for a simply supported 6 meter span slab. Is that clear, Bashita? So basically by going for PT, you can reduce the amount of concrete and make the structure lightweight. What are the advantages? If it's a multi-story scenario, the total dead weight of the structure is less. So you need less concrete and less reinforcement. So there's a particular advantage in going for PT in construction. By going for pre-stressed concrete in construction, we can reduce the amount of concrete, the weight of the structure, the amount of steel going into the structure. And what we do is in the opposite direction, we provide nominal reinforcement. That is the minimum reinforcement. Is that clear? Okay. Then let's look at two-way spanning. Or share the note. So Right. So basically, we look at two spanning steps. You can see this equation. W balanced is equal to 8 PA, YA, or LA squared plus 8 PB, YB, LB squared. So what happens? Let's say we have a slab, 8 meters in one direction, 9 meters in this direction, and the main direction, the other direction. So each direction, the total load is W to be balanced, WB. So part of the load will be balanced by the cables in 9-meter direction, that's this direction. Some of the other cables will be effective in 8-meter direction. So in your opinion, which is the more stringent? Shorter direction is generally stringent. So what we do is, we take an easy way out. We will not worry too much about. And then in the weaker direction, we apply about 1 to 1.2 newtons per meter square. We apply a nominal PT. Then what happens? Then if you are going to use about 180 millimeters, then dead load is 0.18 into 25, 4.5. So let's say we are going to balance dead load. Balanced. So in the long span direction, we are applying a pre-stress. So balanced in the long span direction is 8 PB YB over LB squared. So 180 millimeters, and you have 20 millimeter cover, and we have two ducts of 20 millimeter, another two going in the other direction, 20 millimeter. So this is about 50 millimeter, this is about 30 millimeter. So this is 90 millimeter. So in the shorter direction, this distance is 40 millimeters. So that is 40 millimeters. So WBL balance load 8 PB. You are applying 1 Newton per meter square. So 1 multiplied by 1000 multiplied by 180 divided by 1000. It elapses 180 kilonewton. PT has been applied with an extensity of 40 millimeters. Nice square. 8 into 180, 0.04. So in the shortest span direction, 0.711 can be carried. So in the longitudinal direction, how much you have to carry? 4.5 minus 0.711. So that is 3.78. So this is the stress they have to suppress. Kilonewtons per. So in the other direction, short span direction, you can say W is kind of weight, PE. So we know the W, so we have to find P is equal to W 3.78. L is 8 meters per divided by 8 and divided by E. Eccentricity in that direction is 50 millimeters. 90 minus 90 minus 30, 60 millimeters. This is 90 minus 30 millimeters, 60 millimeters. Three point seven eight. 'So we need a pre-stress of 504 kilonewtons in the other direction. So we have a slab, 9 meters this way, 8 meters this way. And then you have to apply pre-stress. So in this direction we are applying 1 Newton per meter squared. In this direction we have to apply a pre-stress of 504 kilonewtons per meter, and that is equivalent to a pre-stress of 504 divided by 180. So that means we are applying 2.8 newtons per meter square pre-stress in this direction. So now we have a pre-stress. Now we have to check stress conditions. Check stresses. For that, we need to know what is the bending moment in this direction. We also need to know what is the bending moment in this direction. So, and what we have to understand is the behavior of this is different to pre-stress concrete. Pre-stress concrete, the behavior is elastic, whereas in reinforced concrete, the behavior is plastic. You know, slabs are designed by considering E-line theory of base coefficients. So because of those coefficients are different to the elastic coefficients. So they can be certain or redistribution of moments, all kinds of things can be there. So because of that reason, we have to find the bending moments due to loading in each direction. So once you find the bending moment due to loading in each direction, we know the bending moment like this. We know the axial stress, we know the stress due to bending moment. We have to just compare it and then see whether the tension is too much or not. Compression is not a problem in slabs because the pre-stress is low. The only problem is tension. So we have to just see, check and see whether the tension is okay. Is that clear, Bashita? So I'll show you how to find the stress bending moments by using various elastic coefficients next week, because we had this external examiner, we were very busy, lot of things we had to postpone. So because of that, today I'll do only 2 hours of lectures. If you want, I can do another 2 hours tomorrow morning. If you are free, Bashita, can you check with your friends and let me know? Just send me a text message. And I have shared all these notes with you, so just go through the notes. Okay? Right. So any questions on this? So PT is pre-stress concrete. What do you think about pre-stress concrete, Bashita? Do you like pre-stress concrete or do you like RC, reinforced concrete? What is your personal preference? Pre-stress. You are from bridge sector. Is that right? You are a bridge engineer. Bridge engineers always like PT. Why? Tell me the reason. Slim sections, lightweight, high strength materials, and no cracks. Therefore, very high durability. That's why bridge engineers always like PT. Building engineers, they like both RC and PT. So, PT is our future. Why? Concrete is very expensive, steel is even more expensive, formwork is also expensive. So in PT, what are the advantages? We can precast and then go for composite construction. And when you precast, you can minimize the formwork. And then once you have precast members, even the street slab can be supported by using very simple formwork that are actually suspended from the PT beams. So you don't need formwork. In bridge construction, we always hang the formwork from the beam. Is that right, Bashita? Yeah. So pre-stress concrete is our future, not RC. But we cannot do anything without RC. RC is needed, but most of the repetitive structural forms, we should go for PT. PT is a wonderful material. And we can design it when it is continuous, we can design it when it's simply supported, we can design it for a slab, we can design it for a beam. Not only that, we can design it for columns as well. What do you think about columns? Pre-stress concrete columns? What do you think, Bashit? It looks like a foolish idea. Foolish idea, is that right? No, it's not. Why? By adding PT, we can hugely increase the bending moment resistance of column. So in columns we use PT to give the column a very high flexural capacity. So when the column is subjected to some kind of bending, what will happen? It can now take the bending moment. Now to ensure that we get the maximum advantage, we have to go for something like 60, 70, 80 megapascal concrete. The moment you go for very high strength concrete, there's a huge advantage in pre-stress concrete, columns, piles. Engineering Laboratory Services company owned by Mr. Bandara, Engineer Bandara. Do you know this Engineering Laboratory Services? Yes or no? There's a company called, Sri Lankan company called Engineering Laboratory Services. And they have done a lot of work in Maldives. And they have imported piles, spun piles. The spun pile means there's a hole in the middle, circular pile. Circular pile with a hole in the middle. Do you know what is the strength of concrete they have used to cast these in Malaysia? 90 megapascal. 90 megapascal. Can you get 90 megapascal in Sri Lanka? I can tell you, we helped one company in Sri Lanka, and they wanted to get 65 megapascal in 24 hours using steam curing. So Professor Sujiv Levankamage did the work. I helped him with the mix design. He did most of the other work. And we got 65 megapascal in 24 hours. What do you think, Bashita? Do you like to stretch materials to that kind of limits? Bashita? You are there. So we can stretch the material. So if you can get 65 megapascal in 24 hours, can you get 90? Yeah, use a little bit of fly ash and allow it to cure for some more time. And by doing little tricks, 80 or 90 is not a big problem. So that is our future. Our future is using high strength materials, very little material quantity, lightweight materials, lightweight members, but huge strength and strength enhancement by using PT, where the whole section will become effective, and with that you get super durability. And the moment you use fly ash, you don't have to worry about sulfate attacks and chloride attacks. So that is our future. Is that clear? Right, okay, so we'll continue. You can talk with your friends and let me know. Okay? Then I'll stop the lecture and share the lecture with lecture recording with Imanta. Putting it on Google Drive. Okay? Right. Okay, thank you.